Okay, let's unpack this. Have you ever encountered a probability problem that it just defied your common sense?
Oh,
You
absolutely.
know, a puzzle that seemed straightforward, but the answer felt, I don't know, impossibly elusive?
Happens all the time in probability.
Well, today we're doing a deep dive into some really comprehensive lecture notes on probability, and they explore concepts that go way beyond your standard coin flip. It's like revealing a world where intuition can often lead us totally astray,
Hmm.
and where the very fabric of how we measure chance gets truly fascinating. Like imagine this scenario from the notes. Points on a circle. Okay, circumference of one.
Got it.
Now, we group these points into families. Any 2 points are in the same family if you can get from one to the other by, say, rotating an integer step
Okay,
distance.
like adding or subtracting whole numbers wrapping around the circle.
Exactly. Now, here's the tricky part. If we pick a point uniformly at random on the circle, what's the probability that this point is the designated head of its family?
Hmm. Sounds simple enough on the surface.
Right. But the answer, as these notes are going to show us, is, well, it's far from simple. Because this seemingly innocent question, it actually has no consistent answer at all.
Indeed. And these particular lecture notes, they really aim to equip you with uh, the rigorous tools you need to navigate that more complex landscape,
Right.
but doing so accessibly, without sacrificing the depth. Think of this deep dive as maybe your guided tour.
Yeah, a tour into those foundational ideas and the advanced techniques.
Exactly. The stuff that underpins so much of modern statistics, finance, machine learning.
Wow.
Our mission here, as your guides, is really to extract the most important nuggets of knowledge from these advanced materials. We want to give you a kind of shortcut to understanding things like measure theory, different kinds of convergence, limit theorems,
Okay.
powerful bounding techniques, Martingales, Markov chains, renewal theory, even Brownian motion.
That's a lot. What's the math background needed?
Well, we're aiming to keep the core prerequisites pretty minimal. Basically, an undergraduate grasp of calculus and some basic probability should be enough to follow along.
Okay, good.
Our goal is for you to gain this knowledge quickly, but, thoroughly, hopefully with plenty of those satisfying aha moments along the way.
So, okay, to really get our heads around advanced probability, especially those moments where intuition just fails us, we first need to understand the bedrock it's built on. Like, what can we actually measure and what can't we?
Exactly. It starts there.
So, our journey into this fabric of probability begins with something, well, pretty mind-bending.
Hmm.
A non-measurable event. Let's go back to that family heads on a circle example.
Good place to start. It's a classic.
Okay, picture that circle again, circumference 1. We define these families. Points x and y are in the same family if x minus y is an integer.
Like zero point 0.3 and 1.3 and 2.3, they're all effectively the same point on the circle, in the same family.
Right. Now here's the crucial step, and it's a bit theoretical. We assume for a moment that we can choose exactly one point from each of these infinitely many families to be its head.
A representative for each family.
Yeah, let's call it the family head. So the question is, what's the probability that a point x, chosen uniformly at random around the circle, is one of these designated heads?
So intuitively, maybe it's 0 because there are infinitely many points. Or maybe it's some fraction.
You'd think. But the lecture notes walk through this derivation showing why actually none of those answers can be consistently correct. It's pretty
Yeah.
cool. Let's maybe formalize it just a touch.
Let's try. So let A be the event that our random point x is ahead.
Okay.
Now think about any other point y in the same family as x. So y is just x plus some integer wrapped around the circle.
Right.
Because we chose x uniformly, the probability that x is ahead should be exactly the same as the probability that y is ahead. The choice was rotationally symmetric. Let's call this probability x. So PA equals x.
Makes sense. The headness shouldn't depend on where in the family you start.
Precisely. Now, every single point on the circle belongs to exactly one family, and each family has exactly one head. So the whole circle is covered by these heads and their relatives, points an integer distance away.
Okay.
If x is the probability of being ahead, then the probability of being, say, one step away from ahead should also be x, right? Because shifting by one integer just maps heads to other points and non-heads to other points, preserving the measure. Same for 2 steps, 3 steps, and so on.
So the total probability, which has to be 1 for the whole circle.
Right. It should be the sum of probabilities of being ahead, which is x, plus the probability of being 1 step clockwise from ahead, also x. 1 step counterclockwise, also x. 2 steps clockwise, x. 2 steps counterclockwise, x, and so on for all integer steps.
So 1 equals x plus x plus x plus infinitely.
Essentially, yes.
Oh.
If we could just sum these like this, the derivation leads to something like 1x plus 2x summed over all positive integers.
Oh.
Yeah. That equation just, it has no solution for x between 0 and 1. If x is 0, the sum is 0. If x is positive, the sum diverges to infinity.
So you just can't assign a probability.
You can assign a probability x that satisfies the basic rules we expect probability to follow, like countable additivity in this context. The event being ahead is therefore non-measurable. We literally cannot assign a consistent probability value to it using the standard framework.
Wow. Okay, but how did we even get to choose those heads in the first place? You said one from each infinite family.
Now you've hit the really interesting, slightly controversial part. That step, choosing exactly one element from each set in an infinite collection of sets, relies on something called the axiom of choice.
I've heard of that. It sounds powerful.
It is incredibly powerful and very useful in many areas of math. But it's also non-constructive. It asserts existence without telling you how to make the choice, and it leads to some really counterintuitive consequences.
But what?
The most famous is probably the Banach-Tarski paradox. It uses the axiom of choice to show you can, theoretically, take a solid sphere,
Okay.
break it into a finite number of, like, point sets,
Yeah.
very weirdly shaped pieces,
Right.
and then, just by rotating and moving those pieces, reassemble them into two solid spheres, each identical in size to the original one.
Wait, what? That's impossible. You can't double volume like that.
Physically, no.
Hmm.
But mathematically, using the axiom of choice and the nature of these non-measurable sets, it's a logically valid consequence. It just completely breaks our intuition about volume and sets.
So this non-measurable heads event is tied into that kind of deep, weird math.
Directly. And the notes make a point to clarify.
Okay.
If we didn't use the axiom of choice, or if we defined the heads differently, maybe allowing multiple heads or picking the smallest number in each family if that was possible, then the event would become measurable.
So it's super sensitive to the setup.
It's extremely sensitive. It highlights how critical our foundational assumptions are, especially when dealing with infinity, and how easily our intuition can fail when we assume any well-described set must have a well-defined probability or size.
It really forces you to be rigorous.
It absolutely does. It shows why we need a more careful foundation for probability theory than just saying the probability is the ratio of favorable outcomes. That doesn't work when you have things like this lurking around.
Okay, that naturally leads to another thing that always felt a bit weird in basic probability. You know, a uniform random variable x on, say, 0, 1. The probability that x equals any specific value x, like px 0.5, is 0.
Correct, because there are infinitely many points.
But the probability that x falls somewhere in the interval p0x1 is 1.
Also correct.
So, how does that work? If you sum up infinitely many zeros, shouldn't you get 0? It feels like a contradiction.
That's a really common question. And it feels like a paradox, but it's absolutely not a contradiction. And the reason, as these notes state very clearly, is that summation over an interval of real numbers does not make any sense.
You can't just sum over an interval.
Not in the way we usually think of summation, like adding terms in a sequence. Standard summation requires the set of things you're summing over to be countable.
Countable, what does that mean exactly?
It means you can arrange the elements of the set into a sequence, like first element, second element, third, and so on, and eventually list every single element. If you can do that, even if the list is infinite, the set is countable. If you can't, it's uncountable.
Okay, examples.
Sure, the integers.
Yeah.
Totally countable. You can list them 0, 1, nadir 1, 2, nadir 2. You'll get to any integer eventually.
Right.
Even the rational numbers fractions are countable. It seems like there are more of them, but you can use a clever trick like arranging them in a grid, numerator versus denominator, and snaking through diagonally. 11, 21, 12, 31, skip 22, 13. You can create a list that eventually includes every positive rational number.
Okay, I see that. But what about the real numbers in 0, 1, the ones we use for the uniform distribution?
Now that is the kicker. The real numbers between 0 and 1 are not countable. They are uncountable.
And how do we know that?
The notes outline a brilliant proof, again using a diagonal argument, very similar in spirit to the rational number counting, but used here to show impossibility. Imagine someone claims they have a list, an infinite sequence, that contains all the real numbers between 0 and 1.
Okay, like by 1, by 2, by 3, and so on, each written as a decimal.
Exactly. Now we can construct a new real number, let's call it y, also between 0 and 1, that is guaranteed not to be on their list.
How?
We construct it digit by digit. We look at the first decimal digit of y1. If it's, say, a 5, we make the first decimal digit of y that's something different, like a 6. Then we look at the second decimal digit of by 2. If it's a 0, we make the second digit of y1. We continue this down the diagonal, make the nth digit of y different from the nth digit of xn.
Ah, I see. So y must be different from I1 because their first digits differ. It must be different from by 2 because their second digits differ.
Exactly. It differs from every number on their supposedly complete list in at least one decimal place. Therefore, y is a real number between 0 and 1 that was not on their list.
Which means their list wasn't complete after all.
Precisely. And since this works for any proposed list, it proves that no such list can exist. The set of real numbers in any interval is fundamentally uncountable.
Wow. Okay. And that's why summing PXCO over the interval doesn't work.
That's the core reason. You can't perform that kind of summation over an uncountable set. It forces us to use a different mathematical tool integration based on measure theory to handle probabilities for continuous variables over intervals. It's a much more sophisticated but necessary way to define the rules of the game.
So let's talk about those formal rules of the game. The notes call them probability spaces, right?
Correct. A probability space is the fundamental structure. It has 3 key components.
Okay, what are they?
First, you have the sample space, usually written as A, omega. This is just the set of all possible outcomes of whatever random experiment you're considering. Rolling a die, A is 1, 2, 3, 4, 5, 6. Flipping a coin is heads, tails. Picking a number in 0, 1, 1, A is the interval 0, 1.
Simple enough. What's next?
Second, and this is crucial, you have the sigma field, or fifth field, usually denoted by F. This is not necessarily all subsets of A. It's a specific collection of subsets of A that we designate as the immeasurable events, the ones we're allowed to assign probabilities to.
Ah, so this connects back to the non-measurable sets idea. F only contains the good sets.
Exactly. F is structured to avoid those paradoxes. And third, you have the probability measure, P. This is the function that actually assigns a probability value between 0 and 1 to each event A that belongs to the sigma field F.
Okay, so A is the possibilities, F is the questions we can ask, and P is the answers. But what makes a collection of sets a sigma field? Are there rules for F?
Yes, absolutely critical rules. A collection F of subsets of A is a field if it satisfies 3 properties. First, the entire sample space A must be in F.
Okay, the event something happens must be measurable. Makes sense.
Second, if an event A is in F, then its complement A, everything in A that's not an A, must also be in F.
If we can measure the probability of A, we must be able to measure the probability of not A.
Third, and this is the most powerful one, if you have a countable sequence of events, A, and each of them is in F, then their union must also be in F.
So if we can measure individual events, we can measure the event at least one of them happens, even for an infinite sequence.
Precisely. That's countable additivity for the sets themselves. And these 3 rules together also imply that countable intersections of events in F are also in F. It's a closed system under these operations.
Okay, let's make that concrete. Example 1.2 in the notes, AAAB.
Right, and suppose we initially just consider the collection A, B, C.
Is that a field?
Let's check. Is A, B, C in A? No. So,
right.
Nope, not a sealed.
Okay.
Does it satisfy the complement rule? Well, the complement of A, B is C, which is A, and the complement of C is AB, which is also an A. So that part's okay. What about unions? AB. Union C is ABC, which isn't an A.
So it fails on rules 1 and 3.
Correct. Now, the notes talk about the field generated by A, written A. This is the smallest collection of subsets that does satisfy all 3 rules and still contains our original sets A, B, and C.
And what is that in this case?
It turns out to be A, B, C, where is the empty set, the complement of A. You can check. A is in there. Complements are in there. A, B, and C are complements. Unions are in there. A, G, A, B, U, C. It works. It's the minimal structure needed.
Okay, so that defines what we can measure. Now, the probability measure P itself, what are its rules?
P assigns a number to each set in F. It also has 3 rules. First, PAB, the probability the entire sample space is 1, certainty. Second, PA, E0 for any event A in F. Probabilities can't be negative.
It's also standard.
Third, this mirrors the 3rd rule for Severs. If you have a countable sequence of disjoint events, A, arrow, and F, disjoint means they can't happen at the same time, their intersections are empty, then the probability of their union is the sum of their individual probabilities. PAE A equals EA.
Ah, countable additivity for the probabilities.
Exactly. This is super important. It's what allows us to break down complex events into simpler, non-overlapping pieces and sum their probabilities.
Like the dice example.
Okay.
Example 1.4, A emits the 36
Right.
outcomes.
Since A is finite, we can actually let F be all possible subsets, the power set. No non-measurable sets to worry about here.
Okay.
PA is just the number of outcomes in A divided by 36. So P rolling is 7, P1 6, 2, 5, 3, 4, 5, 2, 6, 1. It satisfies all the rules.
Okay, but back to the tricky case. The unit interval 0, 1, we know it's uncountable. What happens if we try to define F and P there?
Well, if we try to let F be all possible subsets, like we did for the finite dice case, example 1.5, we run into trouble.
Because of the non-measurable sets, like the family heads.
Exactly. It turns out you can't define a probability measure P on all subsets of 0, 1 that satisfies our rules, like countable additivity and translational invariance for the uniform case. You inevitably include sets like the one from the paradox.
And what if we try building F just from single points? Like
Yeah.
ESC for all x in example 1.6.
That also fails, but for a different reason. You can only form countable unions and intersections of single points, but an interval like 0.2, 0.4 contains an uncountable number of points. You simply cannot construct that interval event using only countable operations on single points. So you couldn't even ask the probability px is in 0.2, 0.4.
So we're stuck. How do we define probabilities on 0, 1?
The solution is beautiful and standard. We use what's called the Borel sigma field, often denoted B. This is defined as the smallest field that contains all possible intervals, open, closed, half open.
So it includes intervals and anything you can make by taking countable unions, intersections, complements of intervals.
Precisely. It includes a vast collection of sets, pretty much any set you can realistically describe or construct, but it cleverly excludes those pathological, non-measurable sets like the family head set.
Okay, so that's our F. What about P for the uniform distribution?
We use the Lebesgue measure. It simply assigns probability Pxy equals Yx to any interval xy. And because of the properties of seals and probability measures, especially countable additivity, this uniquely defines the probability for all sets in the Borel sigma field B.
And the notes say this setup, the Borel sigma field B and the Lebesgue measure P, is pretty much all you need.
For defining a uniform distribution on 0, 1, yes. It's the standard, rigorous foundation that avoids paradoxes and allows us to calculate probabilities for all the reasonable events we care about in continuous probability.
Okay, that makes sense. And from these basic rules of probability spaces, we can derive useful tools like the inclusion-exclusion formula.
Absolutely. The familiar PABP is entrepreneur plus PAB is a direct consequence. You add the individual probabilities but subtract the overlap because you counted it twice.
But it generalizes.
Oh, yeah. For 3 events, it's PA plus PB plus PB, PAG, plus PAB. And it continues like that, alternating signs for intersections of increasing size. It's a powerful combinatorial tool derived directly from the axioms.
Like in example 1.9, the card problem. Probability of at least one card back in its original position after shuffling in cards.
Exactly. You defined AI as the event that card I is in position I. You want PA, AO, use inclusion, exclusion is the way to calculate that. You need PAI, PAIAJ, PAAA, and so on.
And the probability of any K-specific cards being in place is NK, right?
Okay.
Because the other NK cards can be arranged arbitrarily.
Correct. Inclusion exclusion then provides the systematic way to combine all those terms with the alternating signs to get the final probability. It often simplifies quite nicely.
There's one more property mentioned, continuity of probabilities. What's that about?
It's about how probabilities behave when events themselves converge. Imagine a sequence of events that are increasing, meaning AO, and they converge to a limit event A, which is their union. Or a decreasing sequence, AA, converging to A, their intersection.
Sorry?
The continuity property, proposition 1.13, says that in these cases, the limit of the probabilities equals the probability of the limit, lim PAA. PAN. So probability respects limits of nested sequences of events.
Exactly. It ensures a certain smoothness or consistency. If events are getting progressively closer to a limiting event in this nested way, their probabilities also get closer to the limiting probability. It's a fundamental property that underpins many limit theorems we'll encounter later.
Okay, so we've laid down the rules of the game with probability spaces, sigma fields, measures. We know what we can measure and how. Now, how do we actually use these tools to talk about numerical outcomes of random phenomena? That's where random variables come in, right? Precisely. Random variables are the bridge between the abstract sample space A and the numerical values we're often interested in.
And the lecture notes seem to emphasize understanding their different personalities and how they interact, especially how sequences of them might converge or get close to something.
That's a huge part of advanced probability, yes. Understanding convergence is key. But first, the definition. Fundamentally, a random variable x is just a function mapping outcomes from the sample space A to real numbers.
Okay, simple enough.
But there's a crucial condition. For x to be a valid random variable in our rigorous framework, it must be F measurable.
F being our sigma field of measurable events. What does F measurable mean for x?
It means that for any real number x, the set of outcomes, such that x as that set must be an event in our sigma field F. In other words, the event x must be measurable for all x.
Why is that so important?
Because if XX wasn't an F, we couldn't assign a probability to it. We couldn't calculate PXX, which is the cumulative distribution function, CDF, the most basic description of a random variable's behavior. Measurability ensures we can actually talk about the probabilities associated with the random variable's values.
Okay, let's use example 1.14 again. AABC and FAABC.
Right, and the notes define a potential random variable X where XA1, XB1, XC2.
Is XF measurable? Let's check XA.
Okay, what's XA0? That's the empty set, which is an F good. What's XA1? That's the set of outcomes where X is 1 or less, which is AB in F. Yes, good. What's XA1.5? Still at F. What's XA2? That's ABC is A in F. Yes, good. For any by 2, it's also A.
So for all X, the set XA is one of the events in F. So X is F measurable.
Correct. Now consider Y defined as YA1, YB2, YC.
Okay.
Let's check YF.
Yeah, Y year is in F.
What?
Y1. That's outcomes where Y is 1 or less, which is AC in F.
Let's look at F. No, F is AABC. The set AC is not in our sigma field.
Ah. So Y is not F measurable. We can't even properly ask, what's the probability YA1 in this setup?
Exactly. The intuition the notes give is key. You can always figure out the value of X using just the events in F, but you can't always figure out the values of Y and Z. Because F can distinguish C from AB, but it can't distinguish A from B. X only requires distinguishing C from AB, so it works. Y requires distinguishing AC from B, which F can't do.
Okay, that clarifies measurability. The notes also mention the sigma field generated by X. Oh, X, what's that?
Intuitively, X is the smallest possible sigma field that makes X measurable. It contains just enough information, just enough events, to determine the value of X, or at least to ask all the relevant probability questions about X, like XX.
And this is important for defining independence.
Very important. Formally, random variables XAs are independent if their generated sigma fields are independent.
And what does it mean for sigma fields to be independent?
It means that if you take any event A euro from A event, any event E from X, then the probability of their intersection, all of them happening simultaneously, is just the product of their individual probabilities. PA euro, AA, PA, PA.
So knowing something happened in 8 euro tells you nothing about the probability of something happening in Eros.
Precisely. It's the rigorous way to capture that intuitive idea of no information.
Now, here's something the notes flag as surprising. Remark 1.21. You can have events, A, B, C, that are pairwise independent, but not mutually independent. That seems weird.
It does seem weird, but it's true. It's a classic pitfall. Let's use the standard example they often use. Slightly different from the one mentioned earlier, but clearer maybe. Two fair coin flips, H euro.
T euro. H, 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 T, H, T, each probability 14.
Let A be the event. First flip is heads, H, H, T, H, P, A 12. Let B be second flip is heads, H, H, Hivaros, PB 12. Let C be that two flips are different, H, T, check.
Okay. Are A and B independent? PAH equals 14 and PA 12, 14. Yes, they are.
Are A and C independent? PHT equal 14, and PAPC equals 14, and PAPC equals 14? Yes, they are.
Are B and C independent? PDPC equals 14, and PPC? Yes, they are too. So they're all pairwise independent.
Right. But now what about mutual independence? We need to check PAC against B.
APC means first flip is H and second flip is H, and the flips are different.
Can that happen?
No. If both are H, they can't be different. So AB is the empty set. PAC equals 0.
Well, what is PAP?
That's 12.
Well,
12, 18.
And 0 is definitely not equal to 18.
Ah, so they are pairwise independent, but not mutually independent. Wow.
It's a crucial distinction. You can't just check pairs and assume everything is independent. You need the full product rule to hold for all combinations.
Good point. The notes also mention convolutions, like for geometric random variables. Example 1.22. proposition 1.23.
Right. That's about finding the distribution of the sum of independent random variables. If you flip in coins, each potentially with a different probability of heads, until each is shown heads once, the total number of flips follows a distribution related to the negative binomial. The point is that we can calculate this sum's distribution even with varying probabilities, which is often more realistic than assuming identical probabilities.
Okay, now let's dive into convergence. You said there are different flavors. This seems really important.
Absolutely fundamental. In probability, how a sequence of random variables xn gets close to a limit x isn't a single idea. We need different modes of convergence for different situations. The strongest type discussed here is almost sure convergence.
Almost sure. Written xn a ace x. What does that mean?
It means that the probability of the event that the sequence of numbers xn converges to the number x is equal to 1. P lim xn equals 1.
So for almost every outcome in our sample space, the sequence of values xo converges to x in the usual calculus sense.
Exactly. The almost part is important, though. Remember, remark 1.36. If x is u101, the event x is 13 is probability 0. So pxv 13 equals 1. Convergence only needs to happen on a set of outcomes with probability 1. It can fail on a set of probability 0.
Okay, and there's an equivalent definition, proposition 1.35.
Yes, a more technical one often useful in proofs. XNOS, if and only if, for any tiny positive number ev, the probability that xn stays within ev x for all sufficiently large n, say for all nom, approaches 1 as m goes to infinity. Pxnx for all nom, 1 as m.
It really has to settle down and stay close.
Yes, eventually it gets close and never leaves that n neighborhood again with probability 1.
Now, the big question that often comes up, if xn converges almost surely to x, can we just swap limit and expectation? Is lim exn equals elim xn, which would be ex?
Great question. And the intuitive answer might be yes, especially with this strong convergence, but
Yeah.
example 1.37 shows a definitive no.
Okay, let's break down that example. U is uniform on 0, 1 on xn I u1. E is the indicator function.
Right. So xn is equal to n if u happens to fall in the tiny interval, 0, 1n, and xn is 0 otherwise.
What happens as n gets huge?
The interval in 0, 1n shrinks towards 0. For any specific u0, eventually 1n will become smaller than u.
Right.
Once that happens, the indicator iu1 becomes 0, and it stays 0 for all larger n. So xn becomes 0 and stays 0.
So for any outcome u except the single point u0, which is probability 0, the sequence xnu converges to 0.
Therefore, xn converges almost surely to 0. The limit random variable is just xn.
Okay, so lim xn is e0, which is 0.
Right. Now, what about lim exn? Let's calculate exn.
exn eniu1. The expectation of an indicator is just the probability of the event.
So exn equals n pu1. And since u is uniform on 0, 1, pu1n is just 1n.
Ah, so exn 1n equals 1 for all n.
Exactly. So the limit of exn as n goes to infinity is lim 1.
So we have elim xn equals 0, but lim exn equals 1. They're definitely not equal.
Not equal at all.
What went wrong? Why can't we swap them here?
The problem is the unboundedness of xn. Even though xn goes to 0 almost surely, the values it takes when it's not 0, namely n, can become arbitrarily large. These large values, even though they occur with small probability, 1n, are large enough to keep the expectation at 1. The expectation doesn't converge to 0.
So we need some condition to prevent that kind of blow up in value.
Precisely. And that condition is given by the incredibly important dominated convergence theorem, or DCT, proposition 1.38.
Okay, what does DCT say?
It says, if xn converges almost surely to x, and if there exists another random variable y, which has a finite expectation, AAIEA, such that the absolute value of every xn is always less than or equal to y, i.e. xn o y, for all n and almost all o.
So y dominates all the xn's?
Yes, if those two conditions hold, almost sure convergence and domination by an integrable y, then you are allowed to interchange the limit and expectation. Lim exn equals ex.
That y acts like a safety net, keeping the xn values from running wild in expectation.
Exactly. It provides the uniform control needed. The proof outlined in the notes is quite elegant, using another result called Fatou's lemma to bound the limit from above and below. It's a cornerstone theorem.
You mentioned Fatou's lemma, and there's also the monotone convergence theorem, MCT, proposition 1.43.
Yes, they are related fundamental results often used to prove things like DCT. MCT's perhaps more intuitive. If you have a sequence of non-negative random variables xn that are increasing pointwise to a limit x, xn plus 1 and xnx, then their expectations also converge. Lim exn equals ex.
If a non-negative sequence climbs up to a limit, its average value also climbs up to the average of the limit. It seems reasonable.
It is, and Fatou's lemma gives a related inequality for limits inferior. These theorems are workhorses in measure theory and probability. They're used to prove basic properties we often take for granted, like linearity of expectation holding even for infinite sums, corollary 1.44, and the fact that EXY between EXEY for independent random variables, corollary 1.45, which needs these tools for a rigorous proof involving simple function approximation.
Okay, so almost sure convergence is the strongest. What's next down the ladder?
Before we get to the next convergence type, there's a lemma that's incredibly useful for dealing with sequences of events. The Borel-Cantelli lemma, proposition 1.46.
Okay, what does it say?
There are two parts, but the first part is the most famous. If the sum of the probabilities of a sequence of events, A rho, is finite, by AUL, then the probability that infinitely many of these events occur is 0.
Let me process that. If the total expected number of events happening, which is AEA, is finite, then the chance of seeing infinitely many of them is 0.
Exactly. It's like if you don't expect to see many in total, you definitely don't expect to see an infinite number.
Makes intuitive sense. Is there a converse?
Yes. The second Borel-Cantelli lemma provides a converse if the events are independent. If the events AH are independent and the sum PAH diverges to infinity, then the probability that infinitely many AH occur is 1.
So if they're independent and you expect an infinite number to occur, they will occur infinitely often with certainty.
Correct. Example 1.48 applies this to coin flips. What's the probability the specific pattern HHTTHH appears infinitely often in an infinite sequence of fair coin flips?
Let AJ be the event the pattern starts at flip J. These events aren't quite independent, overlapping patterns, but a related argument or a block argument often shows the sum of their probabilities diverges.
Right. And a version of the converse lemma implies that, yes, PHHTTH occurs infinitely often. Greal 1. Any finite pattern will eventually appear and reappear infinitely often.
Okay, Borel-Cantelli helps with infinite occurrences. Now, the next convergence type.
Convergence in probability, written XNIP.
What's the definition?
It means that for any small positive number, the probability that xn is far from x, meaning xnx, goes to 0 as n goes to infinity. Lim xn for all a0.
How does this compare to almost sure convergence?
It's weaker. Almost sure convergence implies convergence in probability, but not the other way around. Convergence in probability only requires the chance of being far away to become small. It doesn't require the sequence to eventually settle down and stay close forever.
Can we have an example of convergence in probability, but not almost surely?
Yeah, absolutely. Example 1.51 provides one. Consider independent random variables xn such that pxn1 equals 1n and pxn0 equals 1n.
Okay. Does xn converge in probability to 0? Let's check pxn0. If we pick x equals 12, then this is just pxn1.
In pxn1, does 1n go to 0 as n goes to infinity?
Yes, it does. So xn converges in probability to 0.
Correct. Now, does it converge almost surely to 0?
Yeah.
Let's use Borel-Cantelli.
Sure.
What's the sum of the probabilities pxn1?
That's 1n, the harmonic series. That diverges to infinity.
Right, and the events in 1 are independent. So by the second Borel-Cantelli lemma,
The probability that xn1 occurs for infinitely many n is 1.
exactly. If xn keeps equaling 1 infinitely often, can the sequence xn converge to 0 almost surely?
No, it keeps jumping back up to 1. It doesn't settle down at 0.
So there you have it. XNEP and xn does not converge almost surely to 0. This clearly shows almost sure is stronger.
Okay, that's a great example. What's the next, even weaker form?
Convergence in distribution, written x and x.
How is this it involves the CDFs, right?
Yes, we say xn converges in distribution to x if the CDF of xn, fnx, nax, converges to the CDF of x, fx, pxna, for every point x where fx is continuous.
Why only at continuity points of the limit CDF?
Good question. Consider an example. Let xn be uniform 0, 1n. As n gets large, xn gets squeezed closer and closer to 0. Intuitively, it converges to the random variable x in if it's 0, a point mass at 0.
Okay.
The CDF of xn is fnx equals 0 for x0, then nx for 0, x and 1 for 1, 1. The CDF of the limit x0 is fx equals 0, 4 by 0, and fx equals 1 for x0. Notice fx has a jump discontinuity at xr.
Right. F jumps from 0 to 1 at x0.
Now, does fnx converge to fx For any by 0, eventually 1nx, so fnx becomes 1, which equals fx. For any as0, fnx is 0 and fnx is 0, so converges at all x 0.
Yeah.
But what about x0?
Fn0 for all n, but f0 equals 1. They don't converge at x0.
Exactly. They don't converge at the discontinuity point of the limiting CDF. That's why the definition carefully excludes those points. Convergence in distribution only requires the CDFs to match up where the limiting distribution is smooth.
Okay. And how does this relate to the other types?
Convergence in probability implies convergence in distribution, proposition 1.52. The proof essentially uses the fact that if xn is probably close to x, their CDFs must also be close, except possibly near discontinuities. So we have a hierarchy. Almost sure probability in distribution.
And convergence in distribution has a useful property related to expectations, proposition 1.53.
Yes, a very important one.
Yeah.
If x at x, then for any bounded continuous function g, the expectation e to xn converges to e to x.
Why bounded and continuous?
Continuity ensures g doesn't do weird things near discontinuities of f, and boundedness helps ensure the expectations exist and converge nicely, often using DCT in the proof, which involves things like inverse distribution functions. It's a key result for relating convergence of variables to convergence of expectations of functions of those variables.
So, connecting this back, what's the big picture relevance of all these convergence types? The notes mention Weierstrass's approximation theorem, corollary 1.58.
Right, that's a beautiful connection. Weierstrass's theorem says any continuous function on a closed interval like 0, 1 can be uniformly approximated by polynomials. The proof presented in the notes actually uses probability specifically, properties related to the convergence and distribution of binomial random variables, scaled appropriately, to prove this purely analytical result.
Wow. So probability theory provides tools to prove results in other areas of math.
Absolutely. It shows the power and reach of these probabilistic concepts, especially convergence theorems. They aren't just abstract. They have a deep connections and applications in analysis, approximation theory, and many other fields. Understanding these different modes of convergence is crucial for applying probabilistic reasoning correctly.
Okay, shifting gears slightly. Let's talk about long-run averages and behavior. The notes introduce the tail sigma field T, definition 1.59.
Yes, this is a fascinating concept. The tail sigma field T of a sequence of random variables x0, x0 na, contains events whose occurrence depends only on the values of xn for arbitrarily large n. They're independent of any finite initial segment, x0, xd.
So events determined by the ultimate behavior of the sequence.
Exactly. For example, example 1.60, the event limb where the average converges to x is in the tail sigma field. Changing the first million x's won't affect the limit of the average.
Makes sense.
But the event sub GA, the maximum value ever achieved is x, assuming x is finite, is not typically in the tail sigma field. Whether the maximum is x could easily depend on the value of x or x.
Okay. And why is this tail field important?
Because of Kolmogorov's 0-1 law, a truly stunning result.
What does it say?
It says that any event A that belongs to a tail sigma field must have probability either 0 or 1, PA equals 0 or PA equals 1.
No middle ground. For any event determined purely by the infinite tail, it's either impossible or certain.
Precisely. There's no room for probabilities like 12 or 0.7 for tail events, assuming independence, which is often implicit here. The proof is incredibly elegant. A tail event A is independent of any finite prefix x0.xk. As k goes to infinity, this means A must be independent of the entire sequence, which means A must be independent of itself.
Independent of itself, how does that work?
Well, if A is independent of itself, then PA, BA, PA, but AA is just A, so PA, PA.
And the only numbers that equal their own square are 0 and 1.
Exactly. A beautiful, simple argument for a profound result about the certainty of long-run behavior.
That's amazing. The notes also mention invariant events and the ergodic theorem. How do they relate?
Invariant events are closely related to tail events. They are events unaffected by shifting the sequence, like replacing XX with X0s. The ergodic theorem is a major generalization of the law of large numbers, which deals with averages of IID variables. The ergodic theorem allows us to talk about the convergence of long-run averages, like 1 of x, to expected values, even when the variables are not independent, as long as the underlying process satisfies certain conditions related to stationarity and these invariant events. It's fundamental in statistical mechanics, dynamical systems, information theory, anywhere you study systems evolving over time.
Okay, so probability can obviously get super complex. We've seen that, especially when things are dependent or when we're trying to approximate one distribution with maybe a simpler one. These lecture notes introduce some really powerful methods to kind of tackle these challenges head on, right?
Absolutely. When exact answers are hard or impossible, good approximations and bounds are essential. The first major tool here is coupling.
Coupling. What's the basic idea?
The idea is to take two random variables, x and y, which might have different distributions and might be defined on different probability spaces initially, and construct a joint distribution for a new pair, let's call them x,
Right.
living on the same probability space.
Okay.
The crucial thing is that the marginal distribution of x must be identical to the distribution of the original x, and the marginal distribution of e must be identical to the original y. So x dx and e equal dy.
So you're putting them on the same stage, so to speak, while preserving their individual characters.
Exactly. And the power comes from the fact that you have flexibility in how you define their joint behavior. The dependency between x and e.
Right.
Example 2.2 gives a simple illustration. If x and y are both standard uniform 0, 1 variables, you could couple them as u, where u is a single u or a 1.
Yeah.
Here, xu and eu, clearly x du and eu. Or you could couple them as u, a 1. Again, xu is u, a 1, and u is also u, a 1.
Ah, so in the first case, x will always, and in the second, x plus equals 1 always. Different joint behaviors, same marginals.
Precisely. This ability to construct specific joint structures is what makes coupling so useful for comparing distributions.
How does it help compare them? The notes mention stochastically smaller.
Right. We say x is stochastically smaller than y, x test y, if pxt, pyt for all ty tends to take larger values.
Yeah.
Proposition 2.3 shows a key result. If x, y, then you can always construct a coupling, x, such that x error happens almost surely with probability 1.
So the stochastic order guarantees you can build a version where one is always physically below the other.
Yes, it gives a concrete realization of that ordering. Then there's maximal coupling. This is a specific type of coupling designed to make x and s equal as often as possible. It maximizes the probability px.
How often can you make them agree?
Proposition 2.5 gives a nice answer for continuous variables with density functions f and g. The maximum possible probability p you can achieve in a coupling is the integral of the minimum of the two densities, fin, fx, gx, dx.
That integral represents the common overlap area under the density curves.
Intuitively, yes. Now, how do we measure how different two distributions x and y are overall? We use the total variation distance dTV, xy.
Okay, what's the definition of that?
It's defined as the supremum, the least upper bound, essentially the maximum, over all possible events A of the absolute difference between the probabilities pxa and pya.
So it's the biggest possible disagreement in probability they can have for any single event.
Exactly. It's a strong measured distance between distributions. And here's the beautiful connection, Proposition 2.7. The total variation distance dTV xy is precisely equal to the probability that x error 2a and a in maximal coupling.
Wow. So the maximum disagreement on any one set, dTV, is equal to the minimum probability of disagreeing overall in an optimal coupling.
Yes. It elegantly links the abstract distance measure to a concrete probabilistic event in a cleverly constructed coupling. It's a really neat result.
Okay, that's coupling. Now what about Stein's method? This sounds pretty advanced. It's for quantifying approximation accuracy.
It is, and it's incredibly powerful, especially for situations where exact calculations are impossible, but approximations are needed, and you need to know how good the approximation is. Think about the classic Poisson approximation to the binomial.
Right. Lots of trials, n large, low success probability, twice small, constant mean is NP, then binomial NP, Poisson.
Correct. That's well known. But what's less known, and where Stein's method really shines, is that the Poisson can approximate sums of Bernoulli trials even when the probabilities are different for each trial, or even when the trials are not completely independent.
Not independent. That's usually much harder.
Exactly. Dependent trials are notoriously difficult. Stein's method gives us a handle on them. For the independent but not identically distributed case, there's a result called LeCam's theorem. Proposition 2.8. It gives an upper bound on the total variation distance between the sum WS ace, where shear independent Bernoulli, and a Poisson Z with mean LeCam. The bound is dTV WSC.
That seems nice and simple. Sum of squares of the probabilities.
It is elegant, but as Remark 2.9 points out, it can have drawbacks. Consider approximating a binomial 100.1 by a Poisson. The mean is LeCam. Lecam's bound gives ELSG equals 100, 0.1 equals 1.
But DTV is always A1 anyway, so a bound of 1 tells us nothing.
Precisely. The bound is useless in that practical scenario, even though we expect the approximation to be quite good. This is where the more general Stein-Chen method for Poisson approximation comes in.
How does it work differently?
It uses a clever auxiliary equation called the Stein equation for the Poisson distribution. It looks like fk plus 1 kfk, like z, where z is Poisson and a is some set of integers. The magic is that this equation relates differences of a function f to the difference between an indicator function and the Poisson probability.
Okay. How does that help bound DTV WZ?
By manipulating this equation and taking expectations, Stein showed you can express DTV WZ, which is the max difference PWZ, in terms of the expectation of a related expression involving W and this function f. Theorem 2.11 gives a general bound that involves terms like KEW, where vi is roughly W without the ith contribution may be conditioned. This structure allows the bound to explicitly capture dependencies between the terms making up W.
That sounds much more powerful if it handles dependency.
It really is. And proposition 2.12 gives a particularly useful special case. If removing a success can only decrease the total count, like W of I, then DTV WZ, they were var WZ.
Whoa, hang on. The error bound depends only on the variance and mean of the actual sum W.
Yes. Isn't that remarkable? It connects the approximation quality directly to the variance to mean ratio of the thing you're approximating. If the variance is close to the mean, like it is for a true Poisson, the bound is small. If the variance is much smaller than the mean, the bound gets close to 1, less useful. But often this bound is much tighter than Lecam's.
That seems incredibly practical. Are there examples?
Yep, the notes show it recovers Lecam's bound for independent trials. Example 2.13. Then example 2.14 applies it to find the probability of seeing a run of K-heads and coin flips a problem with dependencies. Example 2.15 uses it for the birthday problem, estimating the number of days with no birthdays among people. These showcase its versatility for dependent sums.
And Stein's method isn't just for Poisson.
Not at all. That was just the first major application, Stein-Chen. Stein originally developed it for normal approximation. Theorem 2.16 discusses bounds on the Kolmogorov distance, max difference in CDFs, for sums converging to a normal distribution, often involving terms related to third moments. It also extends to exponential approximations, corollary 2.24 for geometric sums.
What's the general idea that works for all these?
The core idea is always similar. 1. Find a characteristic operator or equation for the target distribution, like fk plus 1 kfk for Poisson or fwwfw for normal. 2. Solve this equation for an auxiliary function f3. Express the distance between your variable w and the target z in terms of an expectation involving w in this function f4. Bound that expectation, often cleverly using couplings or other tricks.
It sounds like a general framework. The notes mention size-bias distributions in this context?
Yes, particularly for the exponential and normal cases. A size-bias version w of a non-negative variable w has a distribution where pwx is related to EWIWX, EW. Essentially, larger values of W are more likely to be sampled to W. This concept arises naturally in Stein's method calculations for certain distributions and helps simplify the resulting error bounds, like in corollary 2.22, which gives a bound for normal approximation related to the central limit theorem.
Okay, let's shift focus now to processes that, evolve over time, where the past influences the future, but maybe in a controlled, specific way. These seem like the tools for understanding everything from stock prices, queuing systems, disease spread, maybe even just a fair gambling game.
Absolutely. This is where we get into dynamic probability, starting with a fundamental concept of conditional expectation.
Right. I remember the basic idea from IntroProb, EXY, the expected value of X, given that we know Y has taken a specific value Y.
That's the intuitive starting point. But the real power comes from thinking about EXY, not just for a specific outcome Y, but as a random variable itself, a function of Y. And the most crucial property here is the Tower property, also called the law of total expectation. EX equals EEXY.
Say that again. The overall average is the average of the conditional averages.
Exactly. You can find the average of X by first finding its average conditional on each possible value of Y, and then averaging those conditional averages over the distribution of Y. It's incredibly useful for breaking down complex expectation calculations.
How is it defined more generally, using those sigma fields we talked about?
The general definition is more abstract but more powerful. EXF the expectation of x given the information contained in the sigma field f, is defined as a random variable, let's call it z, that satisfies two conditions. One, z must be measurable with respect to f, meaning its value is determined by the information in f. And two, for any event a in f, the expectation exia must equal ezia.
Whoa, okay, that's technical. What does it mean intuitively?
It means that z equals exf behaves like x, on average, over any set A that you can define using only the information in F. The Radon-Nikodym theorem from measure theory guarantees that such a Z exists and is essentially unique.
Got it. And it has properties like linearity, proposition 3.4.
Yes, EAX plus by F is AEXF plus BEYF. It also satisfies Jensen's inequality for convex functions EXFO, FEXF. And if X is independent of F, then EXF equals EX, knowing F tells you nothing new about X.
What about proposition 3.6? EXWF if W EXF if W is F measurable.
That's a really useful one. It says if the value of W is already known given the information in F, i.e. W is F measurable, then you can pull it out of the conditional expectation. It acts just like a constant within that conditional world.
Okay, this setup for conditional expectation seems crucial for the next topic. Martingales. You mentioned gambling.
Right. Martingales are the mathematical formalization of a fair game. Imagine Zn represents your fortune after n rounds of betting.
Okay, I want Zn to go up.
Well, a martingale represents a game where, on average, it doesn't systematically go up or down. Definition 3.7 lays out three conditions for a sequence Zn to be a martingale with respect to a sequence of increasing sigma fields, Fn, called a filtration, representing information accumulating over time.
What are the conditions?
First, EZn must be finite for all n. Your expected fortune can't be infinite.
Reasonable.
Second, Zn must be adapted to Fn. This means the value Zn is completely determined by the information available up to time n, I by the events in Fn. You can't know your time and fortune based on future information.
Also makes sense.
Third, and this is the core martingale property, EZn plus 1 Mn equals Zn. Given all the information up to time n, your expected fortune at the next step, m plus 1, is exactly equal to your current fortune, Zn.
Ah. So knowing the entire history doesn't help you predict if you'll be better or worse off on average in the next step. It's perfectly balanced.
Precisely. It's a fair game at every single step, given the past.
What are some examples?
The classic one is a simple random walk where you add up IID random variables, ETH with mean 0, let SN exist n plus men acri plus XN, then SN is a martingale. Think of she as the outcome of a fair coin flip, plus 1 or next in 1. Your total winnings SN form a martingale.
Okay. Any others?
Example 3.10 is important. If the she or IID means 0, variant small ESC, then ZN's SN seen is also a martingale. It's not obvious, but it checks out. Another crucial type is the Doob martingale. Example 3.11. If Y is any integrable random variable and Fn is our filtration, then Zn as En is a martingale.
Wait, the conditional expectation itself forms a martingale?
Yes. As more information Fn becomes available, our best estimate EYFN of Y changes, but the expected value of our next estimate given our current information is just our current estimate. It's a process of refining an estimate under fairness. Example 3.12 shows another one constructed from differences.
Okay, so martingales model fair processes. What about stopping them? The martingale stopping theorem.
This is a huge result. First, we need the concept of a stopping time, n. It's a random time, but with a special property. The decision to stop at time n, the event nn, can only depend on the information available up to time n, EAN, must be an event in Fn.
You can't peek into the future to decide when to start. If you flip coins, you can decide to stop after the first time you see 3 heads in a row. That's a stopping time. But you can't decide to stop just before you're about to lose big.
Exactly. Now, lemma 3.13 shows that if Zn is a martingale and n is a stopping time, the stopped process is Zmin, nn, which follows Zn up to time n and stays constant, is also a martingale. This is a key step.
And the theorem itself, proposition 3.14.
The martingale stopping theorem, sometimes called the optional stopping theorem, states that under certain conditions, crucially, often related to En being finite, and the martingale increments Zn plus 1 Zn being bounded, or the martingale being uniformly integrable, the expected value of the martingale at the random stopping time n is equal to its initial expected value, EZn equals EZ0.
So if you play a fair game, martingale, and you use a stopping strategy based only on the past, your expected final fortune is just your initial stake. You can't beat the system with timing.
Under those conditions, precisely. It's a mathematical proof that you can't beat a fair game with a non-anticipating stopping rule.
That's really powerful. Does it have direct consequences?
Oh, yes. A major one is Wald's equation, Corollary 3.15. If j we I are IID with mean may, and n is a stopping time with finite expectation en, then the expected value of the sum up to time n, ESN x plus xn, is simply EEN.
The expected sum is the expected number of terms times the expected value of each term. That seems intuitive, but is it obvious when n is random?
It seems intuitive, but proving it rigorously requires the Martingale stopping theorem applied to the compensated sum Sn nu, which is a Martingale. It's incredibly useful because En is often easier to find than the distribution of Sn.
And the notes give applications?
Lots. Example 3.16, finding the expected time until a specific pattern, like 0120 is 1, appears in IID data, using Wald's equation cleverly. Example 3.17, a card game, 26 red, 26 black, showing any stopping strategy yields a 12-win probability. Example 3.18, the matching problem, hat check, finding ENN using martingales. Example 3.19, getting approximations for the gambler's ruin probability, hitting A before B. The theorem provides a unified framework for tackling these diverse problems.
What about bounding probabilities for martingales? Like, how likely is it to stray far from the start?
For that, we have concentration inequalities. The Hofting-Azuma inequality, theorem 3.26, is a key one. It provides exponential balance on the tail probabilities, P, Cn01A, for martingales whose differences Zn, Zn1 are bounded.
So if the steps of the fair game aren't too wild,
then the probability of ending up far from the starting point decays very quickly, exponentially fast. Corollary 3.28 gives simplified bounds specifically for sums of independent bounded random variables, which form a martingale. Examples 3.2 and 3.30 apply these bounds to pattern counting and ball and earn problems.
do martingales always just wander off, or can they converge? Martingale convergence?
They can definitely converge. First, let's quickly define sub-martingales. Expected value tends to increase, E Zn A plus 1 AA or Zn, and super-martingales, expected value tends to decrease, E Zn plus 1 AA or Zn. A fair game is both a sub and super-martingale.
Okay.
Lemma 3.34 uses Jensen's inequality to show that if Zn is a martingale and f is a convex function, then fZn is a submartingale. For example, Zn is often a submartingale.
And Kolmogorov's inequality.
That corollary 3.36 is an inequality for submartingales, bounding the probability that the maximum value exceeds some level. But the big result is the martingale convergence theorem, theorem 3.37.
What's it say?
It says that if a martingale Zn has its expected absolute value EZn bounded uniformly for all n, then the limit lim Zn as EZ exists and is finite almost surely.
Wow. So if the expected size of the fortune stays bounded, the fortune itself actually settles down to some specific finite value.
Yes, it doesn't just wander off to infinity or oscillate forever.
Yeah.
And a direct consequence, corollary 3.38, is that any non-negative martingale, like say your fortune in a game where you can't go below 0, automatically converges almost surely to a finite limit. Since Zn for non-negative Zn, Zn is bounded.
That's profound. Fair games under these conditions don't go on being unpredictable forever. They eventually settle down.
It's a very deep result about the stability of these processes. Example 3.39 on branching processes illustrates it perfectly. Let xn be the population size in generation n, and m be the mean offspring per individual. Then Znxne is a martingale. Since Zn is non-negative, it must converge almost surely to some limit z. If m1, the only way for xn to converge is if xn goes to 0, extinction. If m1, z might be positive, implying xn grows roughly like may z exponential growth, or z might be 0, extinction is still possible. The theorem guarantees the limit exists, which tells us about the possible long-term fates.
Amazing. Okay, one more major topic in this dynamic section. Markov chains. How do they differ from martingales?
Markov chains model sequences where the future depends only on the present state, not on the entire past history that led to the present. This is the crucial Markov property or memoryless property.
Whereas for a martingale, the future expectation depended on the present value, but the actual transitions could depend on the whole past via fn.
Right. For a Markov chain, definition 5.1, if xn is the state at time n, the probability of moving to state j at time n plus 1, given the entire history fn, which includes xn1, depends only on the current state xn. Pxn plus 1 plus 1 plus 1 with jxn.
The past before xn is irrelevant for the next step.
Exactly. If these transition probabilities, p xn plus 1 equals j, xn equals I, depend on the time, and we call them stationary transition probabilities, denoted pj. These form the transition matrix P. The n-step transition probabilities, p and ij, are given by the entries of the matrix C raised to the nth power.
Example 5.2 shows something that isn't Markov, xn plus yn plus yn1.
Right, where y's are coin flips. To know the probability of xn plus 1, which is yn plus 1 plus yn, you need to know yn. But knowing xn, which is yn plus yn1, isn't enough by itself to determine y. You also need to know yn1. So the future depends on more than just the present state xn. It violates the Markov property.
Just like Martingales had a stopping theorem, Markov chains have the strong Markov property, proposition 5.5.
Yes. It extends the memoryless property to stopping times t. If you stop a Markov chain at a stopping time t, the process essentially restarts from the state xt, independent of the history before t, given xt.
So the chain forgets how it got to xt when it restarts.
Pretty much. Example 5.6 on queuing losses and example 5.7 on cover times, visiting all states, rely heavily on this property for their analysis. It allows breaking down complex paths at strategic stopping points.
Markov chains have different types of states, right? Classification.
Yes, classifying states is key to understanding long-term behavior. States I and j communicate, if you can get from I to j and back from j to I. Communication defines classes of states. If all states form a single class, the chain is irreducible.
Okay. And recurrent versus transient.
A state I is recurrent if, starting from I, the probability of eventually returning to I is 1. If this probability is less than 1, the state is transient. Proposition 5.8 shows recurrence transience is a class property. All states in a class are the same type.
So you either keep coming back or you might leave and never return.
Exactly. And recurrent states are further divided. Positive recurrent if the mean time to return is finite, and null recurrent if the mean return time is infinite. You'll return eventually, but it takes infinitely long on average. Positive recurrence is also a class property.
This sounds crucial for long-term averages, which leads to stationary and limiting distributions.
Right. Does the probability p and ij of being in state j after n steps, starting from I, converge to some limit, pj, as? If this limit exists and is independent of the starting state I, it's the limiting distribution.
Does it always exist?
Not necessarily. For example, a chain that just alternates between state 0 and state 1, p0, 1, p10 on 1, never settles down. P and 0, 0 is 1 if n is even, 0 if n is odd, no limit. This relates to the period of a state.
Period.
The period d to state is the greatest common divisor of all possible numbers of steps for which p0 you can return to I. If d1, the state is aperiodic. Communicating states have the same period, proposition 5.11. A periodicity is needed for limiting probabilities to exist.
Okay. What about a stationary probability vector?
A stationary distribution, Holmes, is a probability distribution on the states such that if you start the chain with x0 having this distribution, then x0 will also have this distribution, and so will x0. x0 mathematically must satisfy chi, meaning j equals psi p, and tie is 1.
It's an equilibrium distribution the chain doesn't leave.
Exactly. And the connection is theorem 5.1 cornerstone result for an irreducible Markov chain. 1. A unique stationary probability vector exists, if and d, only if the states are positive recurrent. 2. If it exists, then tie j weighs 1, 1, where eta is the mean return time to state j. 3. If the chain is also aperiodic, then the stationary probability, che, is also the limiting probability, chi ax was lemaj.
Wow. That ties everything together: recurrence, mean return times, stationary distributions, and limiting behavior.
It's a beautiful and powerful theorem. The proof outlined involves constructing a related process to find the mean return times.
The notes also mention time reversibility.
That's a special property. Definition 5.19. A chain is time reversible if the probability of seeing a transition IA is the same as seeing ji when the chain is in its stationary distribution. It means the chain statistically looks the same running forwards or backwards in time. This holds if IP Shay equals the JBJ.
And mean passage time bounds, proposition 5.23.
Provides bounds on expected times to reach certain states, useful for specific types of chains, illustrated with a balls and urns example, example 5.24. And finally, yes, the gambler's ruin problem is a classic Markov chain application.
It's clear Markov chains are everywhere. Recommendation engines, finance, understanding these classifications and distributions seems vital.
Absolutely essential for predicting long-term behavior in systems with that memoryless property.
Okay, let's zoom out a bit. We've looked at sequences of states. Now let's look at processes defined more by the times between events or by continuous random movement. How do systems renew themselves? How do random paths unfold? First up is renewal theory.
Right. Renewal theory studies processes that, in a sense, probabilistically restart themselves. A basic renewal process, definition 6.1, is defined by a sequence of intervent times x0, x0 so. These are assumed to be independent and identically distributed IID, non-negative random variables. Think of G as the time between the I-1th and F's customer arriving, or the lifetime of the S light bulb.
So SNS ups plus XN is the time of the nth event, the nth arrival, the nth bulb replacement, and NT is the number of events that have happened up to time T.
Exactly. NT is the counting process. The key idea is that whenever an event occurs, a renewal happens, the process sort of forgets the past and starts over probabilistically, because the next intervent time xn plus 1 has the same distribution and is independent of everything before S.
What can we say about NT, the renewal function, MTD, till T?
Yes, MT is the expected number of renewals by timed. It's always finite if the mean intervent time is FST, and a fundamental result is the strong law for renewal processes, proposition 6.2. As time chi goes to infinity, the rate of renewals NET converges almost surely to 1.
The long-run average number of events per unit time is the inverse of the average time between events. That makes perfect intuitive sense.
It does. Example 6.3 is a bit counterintuitive, though. A strategy to maximize heads proportion by discarding a coin on tails. Because the expected time until tails becomes infinite under this strategy, the long-run rate of tails, 1 tails, goes to 0, meaning the long-run proportion of heads becomes 1.
Because you wait infinitely long on average for the bad event.
Exactly. There's also the elementary renewal theorem, proposition 6.5, which states that the expected rate also converges, ENTTAA. The proof uses Wald's equation in a comparison argument. And naturally, there's a central limit theorem for renewal processes, proposition 6.72. It says that for large T, NE is approximately normally distributed.
With mean to and variance related to and the variance of X.
Mean T and variance to period. It allows us to quantify the fluctuations around the average rate.
What about renewal reward processes, adding value to the cycles?
This is where renewal theory gets really applicable. Suppose that each time a renewal occurs, at time Sn, you receive a random reward, Ro, and the pairs Xn, Rn, Riid. Let Rt be the total reward accumulated by time t.
Okay.
The renewal reward theorem, Theorem 6.8, is a cornerstone result. The long-run average reward per unit time, RTT, converges, almost surely in an expectation, to the ratio of the expected reward per cycle divided by the expected length of a cycle, EROXA.
Average reward rate, average reward per cycle, average time per cycle. Again, very intuitive.
And incredibly useful. Example 6.9 uses it to connect Markov chain stationary distributions J back to renewal ideas, showing J is proportional to the expected number of visits to state J within a renewal cycle back to the starting state. Example 6.mir uses it to find the expected time until a complex pattern occurs by defining rewards cleverly based on overlaps in the pattern.
The notes also define age, AT, and XSYT.
Yes. At any time, ET is the time elapsed since the last renewal event occurred. YT is a remaining time until the next renewal event. Their sum, AT plus YT, is the length of the renewal interval containing time t.
And their long-run behavior.
Proposition 6.12 relates their long-run average values and distributions to the moments of the intervent time x. For example, the long-run probability that the XSYT is less than x is given by the equilibrium distribution, fx, pxy, dkto. The average age and average excess in the long run both converge to EXY8. The proofs often use that clever reward rate trick.
And this connects to queuing theory, Little's law.
Directly. Proposition 6.13 is a general result from renewal reward. Average reward rate equals RR, arrival rate times average reward. Corollary 6.14 applies this to a queue. Think of arrivals as renewals. Let the reward for an arrival be the time that customer spends in the system, W. Let L be the arrival rate. Right. Let L be the average number of customers in the system over the long run. The total reward accumulated per unit time is L. Average time is like total customer hours per hour. So L equals EW. That's Little's law. L will W the WIW. Average number in system, arrival rate, average time in system.
And it holds very generally.
Amazingly generally. It doesn't depend on specific arrival or service distributions, just the limits exist. It's fundamental.
What if the renewal process has exponential inter-arrival times?
That's the special case called the Poisson process. If xi, exponential, then nt follows a Poisson distribution, proposition 6.16. This follows from the memoryless property of the exponential.
And the Poisson process has special properties, stationary and independent increments.
Yes. Stationary increments means pnt plus snt depends only on the interval length s, not on the start time t. Independent increments means the number of events in non-overlapping time intervals are independent random variables.
And proposition 6.17 says the Poisson process is unique in this.
It's the only counting process with stationary independent increments and continuous inter-arrival times. The proof shows these properties force the inter-arrival time to be memoryless, which means it must be exponential, thus defining a Poisson process. It's the fundamental model for purely random events occurring at a constant average rate over time.
Okay, from discrete events in time to continuous random movement. Brownian motion.
Yes, the continuous time limit of a random walk. It's a process BT with continuous paths, stationary independent increments, and where BTE is normally distributed with mean zero and variance TS.
The notes have a cool way to construct it, recursively moving midpoints.
Yes, it's a constructive approach on 0, 1. Start with B0, 0, B1 from N0, 1, then find B12 by adding a scaled N0, 1 random variable to the average B0 plus B1, 2, then find B14 and B34 by adding scaled normals to the averages of their neighbors, and so on. Figure 7.3, 7.5 show how the path gets increasingly jagged.
And this shows the self-similarity, remark 7.3.
Exactly. If you zoom in on a piece of the path, it looks statistically the same as the whole path. It's a fractal. Proposition 7.4 confirms it's a martingale, has stationary independent N0 TS increments, and BT N0 T. Proposition 7.6 rigorously proves the paths are continuous with probability 1, despite their infinite wiggliness.
What about remark 7.7 on measurability? Is BS is not continuous a non-measurable event?
It clarifies that while the set of discontinuous paths might seem problematic, it's a subset of an event that Proposition 7.6 shows has probability 0. So we can consistently assign it probability 0. It doesn't cause the same paradox as the family headset, which involved positive probabilities.
Does Brownian motion have a strong Markov property?
Yes. Like discrete Markov chains, it restarts probabilistically at stopping times t. The process, BT plus t, behaves just like a fresh Brownian motion, BT, independent of the path before t.
Proposition 7.9 gives a surprising probability.
Biceps, BS. Yes, the probability that the maximum value reached by time t exceeds x is twice the probability that the value at time t exceeds x, p nanos as x, equals 2 pdtx. This is the reflection principle.
Useful for finance, path-dependent options. Example 7.0.
Absolutely. Options like lookbacks, payoff depends on max price, or knockouts, option expires if price hits a barrier, depend directly on the supremum or infimum of the price path, often modeled by Brownian motion. The reflection principle helps value these. It also aids Monte Carlo simulation efficiency, using control variates based on self-similarity.
Can we embed other variables in Brownian motion?
Yes, remarkably. Propositions 7.1 and 7.12 analyze hitting times t for boundaries A and D, giving EBT, ET, and hitting probabilities. But proposition 7.13 is profound. For any random variable x with mean 0 and variance routes, you can find a stopping time t such that bt has the exact same distribution as x, and the expected stopping time et is exactly tap.
You can represent any mean 0 variable by stopping a Brownian motion at the right random time.
Yes. The proof involves constructing t as the first time bt hits one of two cleverly chosen random boundaries, y or z. It's an amazing embedding result.
And this leads to a generalized CLT. Proposition 7.15.
Correct. It shows that for stationary ergodic sequences GA with conditional mean 0 and conditional variance 1, the normalized sum SNCH converges in distribution to N01. The proof relies on embedding the partial sums ISA-AN within a Brownian motion path and using properties of stopped Brownian motion and the ergodic theorem. It showcases the unifying power of Brownian motion.
Okay, last section. We've seen how complex things can get. Sometimes finding exact probabilities or expectations is just too hard. That's where bounding techniques come in, right? Giving useful estimates when the exact answer is out of reach.
Exactly. These notes cover several powerful bounding methods. We've already seen Jensen's inequality pop up a few times.
Remind me, for convex functions f, EEX, FEX.
And the reverse for concave functions. Simple, but widely applicable for getting quick bounds using only the mean and convexity.
What about importance sampling and Chernoff bounds?
Importance sampling is a technique, often used in simulation, to estimate expectations under one distribution by sampling from another related distribution. It can also be used theoretically to get bounds. Chernoff bounds, section 4.4, are a specific application providing exponential bounds on tail probabilities, like PXC.
They use the moment-generating function MPETX.
Down is PXC-ECTMT, optimized over T0. It gives very tight bounds for sums of independent variables, often much better than bounds based only on variance like Chebyshev's. Example 4.0 uses it to analyze cell survival probabilities.
What other bounds are there? Second moment and conditional expectation inequalities.
Right. The second moment method uses variance to bound probabilities related to Chebyshev. Proposition 4.15 gives a useful lower bound on PW0 using conditional expectations. PW0. UWO. Example 4.16 applies this to system reliability problems, finding the system functions, which is the probability some W is positive.
And the min-max identity, section 4.6.
This relates the maximum of a set of variables to sums and differences of expectations of minimums of subsets. It can be used to get bounds on the expectation of the maximum, useful in problems like the coupon collectors, example 4.19, estimating how long until you see the last distinct coupon.
Finally, stochastic orderings, comparing random variables without full distributions.
Yes, several ways to say one variable x is larger or riskier than y. 1, stochastically greater xt, or pxt, p-way t for all t, x tends to be larger. 2, hazard rate order, x or y. The failure rate of xt, pft, pxt is less than or equal to it. X is less likely to fail given it has survived to t. 3, likelihood ratio order, x, u, or y. The ratio of densities fxt(x) is non-decreasing. Strongest order implies x is relatively more likely to take larger values. 4, reverse hazard rate order, x, u, or y, related to the time to failure density divided by the CDF.
Why are these useful?
They allow qualitative comparisons. If you know x or y, you know x tends to last longer in a reliability sense. Theorem 4.23 gives equivalent definitions based on conditional distributions, e.g., x or y, fxxt ost yyt. Corollary 4.24 shows a hierarchy. LR order, AH order, ST order. Hazard rate order is separate, but also implies ST order. The notes also mention increasing hazard rate, IHR variables, things that wear out over time. Proposition 4.25 connects IHR to the property that the remaining lifetime XTXT stochastically decreases as P increases.
Hashtag, tag, hashtag, outro.
Wow, okay. What a deep dive that was.
Yeah.
Seriously, from those paradoxes of non-measurable events that just mess with your head.
Right. They really challenge your intuition.
All the way through measure theory, the elegance of Martingales, Markov chains, renewal theory, and that fractal weirdness of Brownian motion.
Yeah.
These lecture notes really cover some ground.
They absolutely do. It's a journey into the sophisticated machinery needed for modern probability. We saw how measure theory gives us that rigorous foundation, avoiding the paradoxes.
We explored all those different ways random sequences can converge almost surely in probability and distribution and why the differences matter. And we looked at powerful tools for approximation and bounding, like coupling and Stein's method, that let us get answers even when systems are incredibly complex or have dependencies.
And the connections to the real world are just everywhere. Machine learning, finance, cues, population dynamics. It really shows how these, sometimes very abstract mathematical ideas actually describe and illuminate how things work.
It's a beautiful interplay between abstract theory and practical application.
Yeah.
Which leads us to maybe a final thought for you, the listener.
Okay.
The next time you hear a statistic or a probability claim, maybe pause for a second. Are you thinking about whether the event being discussed is even measurable in a consistent way?
Huh. Like, could there be an axiom of choice issue lurking underneath?
Maybe not always that dramatic. But what assumptions are being made? Independence, boundedness. Which type of convergence are they implicitly talking about if it's a long-run claim?
Right. Because as we've definitely learned today, the world of probability is way richer and honestly far more surprising than it often seems on the surface. It really rewards digging deeper.
It certainly does.
So we definitely encourage you to maybe revisit some of the examples that caught your ear today, or perhaps even seek out these kinds of lecture notes yourself. There's always more to explore in this fascinating world.